This video is about the curl right-hand rule, and we use the curl right-hand rule when a moving current induces a magnetic field. We use the curl right-hand rule because an electric current moving in a wire actually induces a magnetic field. And to find the field's direction, we use this curl rule. So you can see that when the current induces a magnetic field, the magnetic field exists in a circle around that current. So to find the direction of that circular magnetic field, if we hold up our right hand in that symbol and say that the thumb points in the direction of the current, then the magnetic field is going to curl around in the direction that our hand is curling, like that. The curl right-hand rule also works in reverse. If we have a current moving in a circle, it induces a magnetic field coming out of the center of the circle that follows the direction of our thumb, like this. And both right-hand rules can also be flipped in terms of which event is causing which. Current induces a magnetic field, and a magnetic field also induces a current. This is actually how most of our electricity is generated. So I'm now going to transition to a separate video where I'm solving some examples of using this rule on a piece of paper. Okay, in this video we're going to use the curl right-hand rule to find the induced magnetic field from an electric current. So I'm going to have my right hand in the shape of that curl symbol, and we're going to see what we can do. So starting up here, I can see that I have a current going straight up. So that means that I'm going to place my thumb pointing up and see how my hand curls around either side of the page. So I can see right away that on the right hand side, like on this side of the current, my curl is going into the page. And when I hold my thumb up here, the curl is coming out of the page like this. So that means that for the induced magnetic field here, on the right-hand side, it's going into the page. And on the left-hand side, it's coming out of the page. What's actually happening here is that this is forming a kind of circular magnetic field where it's coming out like this, going back in like that, circling around, coming back like this, but we can't really represent that accurately on a 2D surface, so we just record where it's coming out and where it's going in. So that's what that would look like. For the second problem, I can see that the current is coming straight out of the page, so if I hold my thumb coming straight out, I can see that my fingers are aiming in a counterclockwise direction. And if I just follow that along, it's always going to be counterclockwise. So that means that the induced magnetic field is going to be going this way in a counterclockwise direction. For this one down here, I can figure out what's going on inside the field and outside of the field, and this time I'm going to flip the rule and say that I'm going to use the rule where my curl represents the current and my thumb represents the magnetic field that's induced by that current. So if I follow my fingers along this way, I can see that inside of the circle specifically, like inside of this circle, my thumb is always pointing up. So that means that inside of the circle, the field is pointing up out of the page. And if I follow the curl rule like this around this way, and I'm just following my thumb around in a circle, I can see that outside of the circle, my fingers are always pointing into the page. So that means that outside of the circle, the induced magnetic field is going to be pointing into the page specifically. Finally, this one's a little weird. You can see that the current is going up around this coil and going sideways this way as it winds around. So if I curl my hand like this, because I can see it starts off, it seems closer to me and then farther away, closer and then farther away. So it's going to curl like this. So I can see that the magnetic field induced inside of that coil is going to point in this direction. So that's how you would find the induced magnetic field direction from the direction of the current that's inducing it.